Imagine you and your friends just got into a fight. Everyone's mad and the group chat goes silent. You all just need space. One goes to the student center, another storms off to Gilman, and someone else grabs food at FFC. And after a while, the distance helps. The energy calms down and balance slowly returns. In every friend group, people need space. And in chemistry, electrons do too. That's the core of VSEPR theory, or valence shell electron pair repulsion. Every electron pair around an atom carries the same negative charge. Since like charges repel, they push away from one another, arranging themselves as far apart as possible. That arrangement determines the molecule's shape, which keeps the system lowest in energy and most stable, similar to finding peace after a fight. Let's look at some specific examples. First, we have the CO2 friend group. You're the central carbon and you have two friends, one on each side, but there's tension. Both friends, the oxygens, are mad and don't want to look at each other, so they stand as far apart as possible. One on your left, one on your right, 180 degrees apart. That's linear geometry, like carbon dioxide. Your two strong double bonds are zones of negative charge, and since they repel each other equally, the group arranges into a straight line, maximum distance, minimum drama. Then there's BF3. Now you're boron, and you've got three friends. You all want to keep things calm after last week's argument, so everyone grabs a seat around you in a triangle, 120 degrees apart. That's trigonal planar geometry, like boron trifluoride. Three bonds, all equal, lying flat in one plane. Then there's CH4. Now you're carbon, and you have four friends, all equally close, all trying to move past the last fight. You decide to hang out, but everyone still wants their space. So you all move into 3D space. One friend sits above you, one below, and the other two hang out diagonally to the sides. Everyone's perfectly spaced 109.5 degrees apart. No one's too close, no one's left out. That's tetrahedral geometry, like methane. Carbon forms four equal single bonds with hydrogen. Each bond represents an area of negative electron density, and the repulsions are perfectly balanced. It's the ideal friend group dynamic. Everyone's chill, and the group is stable again. But things don't always go according to plan. Let's look at NH3. You're nitrogen, and you have four electron groups around you, three bonded friends, and one extra friend who's kind of fake. This fake friend, the lone pair, pretends to be part of the hangout, but doesn't actually bond with anyone. They stay close to you, whispering behind everyone's back, radiating negative energy that makes the others uncomfortable. That lone pair is a concentrated pocket of electrons sitting close to your nucleus. Because it's not shared in a bond, it's more dense, and that extra electron density means stronger repulsion. Your three real friends, the hydrogens, feel that energy and move a little closer together to stay away from the fake one. The tetrahedral spacing of 109.5 degrees shrinks to about 107 degrees, forming a trigonal pyramidal shape. That's ammonia. Three true bonds, one two-faced lone pair, and a slightly squished shape caused by all that extra negativity. In the end, VSEPR theory is about finding balance after conflict. Every electron pair, like every friend, carries a bit of negativity. When they crowd together, tension builds, but when they spread out, the energy lowers and the whole group becomes stable again. That's what molecular geometry is all about. Atoms are people arranging themselves in the way that keeps things calm, balanced, and at peace. So next time your friend group needs space after a fight, remember, you're not drifting apart. You're finding stability. Because even in chemistry, sometimes the only way to stay bonded is with a little bit of distance.